Okay, let's just jump right in. Welcome to this explainer on modern PCB design. I want you to picture this for a second. Massive, high-tech manufacturing plants, automated surface mount assembly lines moving at lightning speed, and robotics dropping microscopic components onto densely packed, multi-layered boards. It's incredible, right? The hardware that literally runs our world doesn't just magically appear out of thin air. So today, we're tracing that entire journey. We're going from raw physics, the absolute foundation of electrical theory, all the way to physical, industrial-scale manufacturing. Whether you're an embedded systems developer, a hardware engineer, or just starting out as a trainee, this explainer is designed to bridge that critical gap between the schematic theory on your screen and real-world execution. Let's get into it.
Here is our roadmap for today. We're going to hit the PCB design lifecycle, jump into the fundamentals of magnetic induction, tackle component selection and filtering, look at electromagnetic system simulation, and wrap it all up with fabrication and industry standards.
All right, Section 1, the PCB design lifecycle.
To kick things off, we really need to establish the sheer complexity and honestly, the incredibly high stakes of modern hardware engineering. Think about the crazy range of applications we're dealing with today. We're talking high-precision GPS RTK boards, massive IoT data loggers, ultra-sensitive biometric sensors, and even satellite communication modules. Designing for these isn't just about connecting dot A to dot B. You need a deep, uncompromising understanding of high-frequency RF routing and embedded processing. You're engineering robust physical pathways for mission-critical data.
Moving right along to Section 2, Fundamentals of Magnetic Induction.
You see, to build these advanced systems, we absolutely cannot ignore the basics. We have to start at the foundational physics of power transfer. At the heart of power management is the transformer, working right off Faraday's law of mutual induction. A changing magnetic field in your primary coil induces a voltage in a secondary, completely electrically isolated coil. There are literally zero moving parts here. It's just the pure physics of electromagnetism letting us seamlessly and safely manage power distribution before it ever touches our delicate integrated circuits. Now, here's the catch. While we can easily manipulate voltage up or down to suit whatever our circuit needs, we can't just magically create more power out of nowhere. It's a strict balancing act. If you step up the voltage, you have to step down the current proportionally, and vice versa. That's just the conservation of energy at work. These equations lay it all out. Your turns ratio perfectly dictates your voltage ratio, and your electromotive force, or EMF, relies heavily on that rate of change. But really, what this shows us is that your transformer's efficiency comes down to managing physical, real-world realities. Specifically, you're fighting copper losses from resistance and iron losses from magnetic hysteresis. Honestly, managing those losses, that's exactly what separates a sloppy power supply from a robust, industrial-grade one. Okay, actually, listen up, because this is a fundamental rule that catches so many beginners off guard. Transformers do absolutely not operate on steady-state DC voltages. Remember how they need a changing magnetic flux to induce voltage? Well, steady DC current gives you zero change. So if you accidentally hook up a primary winding to a DC supply, well, your inductive reactance drops straight to zero. Without that impedance, you get a massive instantaneous current surge that will literally burn out your copper component. Please don't do that.
Which brings us to Section 3, Component Selection and Filtering.
Let's zoom way in now, right down to the board level. Once we've safely stepped our power down to logic levels, we need that power to be flawlessly clean. When you're dealing with high-speed digital logic, especially clock distribution circuits, noise is your absolute worst enemy. We're looking at some engineering application data from Texas Instruments here, showing exactly how bypass and filter capacitors are used to crush AC ripple and stop dangerous voltage droop in our DC circuits.
And notice, a single bypass capacitor just isn't going to cut it in modern high-speed designs. You need a multi-value capacitor array. Why? Because every single capacitor hides parasitic equivalent series resistance and inductance, ESR and ESL. So you use a large bulk capacitor, like a 47 microfarad, to catch low-frequency voltage droops. Throw in a 0.1 microfarad for the mid-range, and add a tiny 0.01 microfarad cap for the ultra-high frequencies. By teaming them up, you effectively target a massively wide noise bandwidth.
I absolutely love how organized this approach is. TI doesn't leave you guessing. They provide a strict 5-step mathematical procedure to nail down the perfect bypass capacitance. You figure out your max expected current step change, weigh that against your noise budget, crunch the numbers on your wiring inductance, and boom, you calculate the exact bypass value you need. It totally takes the guesswork out of signal integrity. Let's put that math into perspective really quick. Imagine you've got a board with 50 gates, and they all simultaneously switch a 15 picofarad load in just 2.4 nanoseconds. If you plug that into the TI formula, you generate a sudden current step change of exactly 1.03125 amps. Over a full amp in nanoseconds, your power supply wiring and your filter array absolutely must be designed to absorb that instantaneous surge, or your whole system is going to crash hard.
Next up, Section 4, Electromagnetic System Simulation.
Before we ever spend a dime printing a physical multi-layer board, we absolutely have to move to digital prototyping. We need to hunt down electromagnetic interference and thermal issues first. This is where heavy-hitting industry software like ANSYS Maxwell steps in. It gives us highly advanced physics solvers to precisely characterize nonlinear transient motion. Whether you're tracking DC conduction on your board traces or 3D magnetic transients from an onboard actuator, you've got to solve it digitally first.
And simulation tech is getting incredibly smart. Let's look at slice-only technology. Historically, simulating a whole board could take days, right? But now, by using non-planar boundary conditions, the software only has to solve one small cyclic slice of a massive 3D geometry. It then replicates the results perfectly. This dramatically speeds up rendering times and actually increases accuracy because you eliminate math errors on matching boundaries. It's a total game changer for rapid prototyping.
All right, our final stop, Section 5, Fabrication and Industry Standards.
We've done the physics, picked the components, and simulated the whole system. Now we translate those digital dreams into physical, manufactured reality. And let me tell you, modern fabrication is wild. We aren't just etching copper in a garage anymore. Top-tier manufacturers are pulling off high-density interconnects, rigid flex boards that literally bend to fit inside your smartwatch, and impossibly small blind and buried microvias. You need this level of incredibly dense, complex routing for today's aerospace, automotive, and wearable tech.
But here's the reality check. Just building it isn't enough. It has to be reliable. Bodies like the IPC lay down the law with rigorous international standards. We're talking IPC A600 for base acceptability, IPC Class 3 for life-critical electronics, or AS9100D for aerospace. Adhering to these codes ensures your board won't just look pretty on a lab bench. It'll actually survive the extreme thermal, mechanical, and electrical beating of a real-world deployment.
So, that's the whole pipeline. From the raw physics of magnetic induction to complex 3-capacitor arrays, through advanced digital simulation, right down to strict industrial-grade fabrication. Understanding this full life cycle is exactly what empowers you to push the boundaries of what's possible in hardware engineering. It's a challenging field, for sure, but man, is it rewarding. So I want to leave you with this thought today. Armed with this complete understanding, what are you going to build next?